An estimator turns a dataset into an answer. For a coin, the MLE is the sample proportion. Fix the true probability at 0.6, generate 8 flips, and place a dot at the estimate. Repeat, the wide yellow cloud is the estimator's sampling distribution. Increase the sample size to 32, then 128. The cloud tightens around the true value. This is consistency. Under suitable assumptions, the estimator settles toward the data-generating parameter as information accumulates. After rescaling the remaining error, the cloud also becomes smoother and more bell-shaped. Under regularity, the MLE is approximately normal for large samples. This is a repeated sampling statement, not a claim that one likelihood curve is a probability distribution. A broad likelihood changes slowly, so nearby parameters are hard to distinguish. As information accumulates, the local peak sharpens and the horizontal uncertainty scale contracts. Observed information is the negative second derivative of the log likelihood we actually saw. Fisher information averages this local sharpness over repeated datasets from the model. We can derive that expectation in a simple case, or approximate it by simulation. More information means less attainable sampling variation. With several parameters, sharpness depends on direction. A narrow direction is well informed, a wide direction is weakly informed. Zero curvature signals a direction the data cannot identify. Can an unbiased estimator have a cloud narrower than the information permits? Under regular conditions, the Kramer-Rao inequality says no. As the candidate variances descend, inverse Fisher information stops them. The line is a floor, not a promise that every estimator reaches it. For the coin, the MLE is the sample proportion. Its variance equals the probability of heads times the probability of tails divided by sample size. Inverse Fisher information gives the same expression. Here the MLE reaches the bound exactly.
So the MLE always has minimum variance.
No, finite sample MLEs can be biased or irregular. The broad claim is asymptotic. In a smooth, identifiable, correctly specified model, the MLE approaches the inverse information limit as sample size grows. The conditions carry the conclusion. Now keep heads, tails, heads fixed. The likelihood peaks at 0.75. A Bayesian adds a prior density for the probability of heads. This one gently favors the middle. Bayes' rule says to multiply prior and likelihood at each candidate value. We can do that on a numerical grid. With no special algebra, divide the product by its total area and the normalized posterior appears. Its area is 1. It is a probability distribution for the parameter, conditional on this model, this prior, and these observations. The likelihood peak gives the MLE at 0.75. The posterior mode gives the map near 0.67, while the posterior mean is 0.625.
Which point is the Bayesian answer?
The posterior is the answer. A point is an additional summary, often chosen for a particular decision. Sweep inward from the tails and keep 90% of the posterior mass. Conditional on our assumptions, this shaded region has 90% posterior probability. For a continuous parameter, probability is area, not curve height. The two probability statements now separate cleanly. A frequentist fixes the true parameter, repeats the data, and judges an interval procedure by its long-run coverage. A Bayesian conditions on the observed data and uses posterior mass to represent uncertainty about the parameter. A full posterior makes it direct to propagate uncertainty into predictions. Nonlinear quantities, or decisions, a prior can also stabilize sparse data. But the answer inherits the prior and model and usually costs more computation. Neither framework makes a poor model true.